Hello everyone, in this video we will be looking at all the topics from each and every chapter in the syllabus in a very short way. I have prepared a very concise summary of every single chapter for you guys so that whatever we discuss in this video, if you remember only those points, only those topics, only those equations, formulas, results, whatever, then you will be able to solve questions very quickly because those memory will be very fresh in your mind and you can easily recollect whenever you see a connection with any one of these topics that we have discussed in a question. You will easily be able to retrieve that information from whichever part of your brain it has been stored in and apply it, solve the question quickly and move on to the next. Our aim here is to only collect a very few key components from each chapter so that simply keeping them in mind, we will not only be able to apply them very easily, but the rest of the chapter will also make much more sense in terms of the concepts that we have seen. So let's start. First chapter is kinematics. You need to only know the relation between instantaneous velocity, instantaneous position and instantaneous acceleration. In the case of one-dimensional motion, they are very straightforward. In the case of two-dimensional motion, what we do is simply we divide the motion into two perpendicular components, x component and y component we call them, and the instantaneous velocity components, acceleration components and the displacement components can be related to each other just the same way as a one-dimensional motion, and we can combine the entire motion vectorially by stating the x and y components of each quantity separately. If you remember just this much, then you will be able to from scratch solve every single problem in kinematics. They all use the same basic principles, just the particular case of motions will be different. For example, for a constant acceleration motion, we get our three famous equations: v equal to u plus at, s equal to ut plus half at square, and v square equals u square plus 2s. All those three famous equations we simply get by keeping the value of acceleration constant so that velocity becomes linearly proportional to time. That's the only thing, which is why just these key concepts, if you keep in mind, you will be able to solve the entire chapter very easily. But some standard relations you need to know is the relation for relative velocity between any two observers. If we have two observers A and B, both having their own motions, their own velocities, their own accelerations, then we can define the relative velocity or acceleration of these objects simply by subtracting the velocity of the observer. So for example, if we look at the velocity of A with respect to observer B, we will simply write the velocity of A with respect to a stationary frame like the ground and subtract the velocity of the observer himself, that is B, and easily get the relative velocity in a vector notation. Now this is useful because if you have the vector form, then scalar forms also, depending on the situation, you can easily be able to see on a problem by problem basis. And projectile motion is a very important component of kinematics. Most of the questions that deal with only kinematics will be from projectile motion. Some might be from relative motion like riverboat problems and rain van problems, but the most famous are projectile motion problems. And if you know the basic formulas of a simple projectile motion, if we launch a projectile with a velocity u and an angle theta with the horizontal, then equation of trajectory is the master equation that governs the entire motion of the particle. If you can memorize this equation, or at least if you know what this equation represents, what each and every term means, what does this mean for special cases, then you don't even need to remember every other result. So you have a choice. You can either remember the equation of motions, or you can keep in mind every single quantity, which is easier to memorize than the equation of motion, but information is stored the same. For example, in the equation of motion, if you substitute the maximum height at height maximum in the y coordinate and half of the range in the x coordinate, then you will get this expression. Simply substituting the value of x and y into the equation of trajectory will give you this expression. Similarly, by substituting y is equal to 0 in the equation of trajectory, you will get the value of the maximum range of projectile. Time of flight also you need to remember, it is simply 2 into vertical component of velocity initially upon g, of course. Again, most questions will be from kinematics, so it is important. Most questions in kinematics will be from projectile motion. So if you remember these results, then you will be able to solve questions very, very quickly. You won't have to keep deriving every single result as you are writing the exam. Now, next chapter, laws of motion. Again, basic principles. If you understand, then this chapter is wholly driven by problems. The more problems that you practice from this chapter, the more easier this chapter will be in your exam. So there is not really any point in remembering anything from this chapter, but the basic flow of logic of the chapter, the basic principles that we use to solve problems, that we should just take a look very, very quickly. We define two quantities. The momentum is basically the amount of motion that any object has. Simply, the speed or the velocity is not enough to describe the motion of a particle, because a particle has a component known as inertia. That also affects the motion of the particle, because this quantity inertia defines how the particle will interact with change in motion. Inertia is basically the resistance to the change in motion. So to define motion accurately, we need the product of inertia as well as the movement of the body. So product of mass and its velocity will give us the exact amount of motion that is contained. So if anyone asks you, how much motion do you think is in that car which is moving, then you will not tell them the speed of the car. Instead, you should tell them the momentum. Mass of the car also plays a very, very important role in the motion of the car. Don't forget this. And we'll define force as another quantity that can change the motion of the object. Hence, force is defined simply as the rate of change of momentum. Because remember, momentum is the accurate quantity that gives us the amount of motion. So if the motion is being changed, then the quantity momentum has to be changing. And how much momentum changes depends on how much force we are able to apply on any moving objects. This is simply the second law of Newton. And if you substitute the fact that momentum of an object is constant, that is, object is undergoing constant motion with the same speed in the same direction, they are not changing, then force has to become zero, because for a constant momentum, the rate of change of momentum will also be zero. That gives us the first law of Newton, that is, if an object is moving under uniform motion, then it should have zero net external force acting on it. So first law of Newton is simply a special case of the second law when momentum is constant, but nonetheless the concept is also important. And if the mass of the object does not change, that is, it is not a variable mass object, the mass is fixed with time, then the rate of change of mass we can neglect, and force simply becomes the mass of the object into the acceleration of the object. This expression F equal to ma is the most important expression to be taken away from this slide, because while solving problems, we will mostly be using F equal to ma to generate equations of motions. That we will see in just 2 minutes. एक बार यहाँ पे एक कट ले ले, पानी पीना है मेरे को. यहाँ से वापस शुरू करते हैं. So here we have seen that the first law of Newton basically defines motion and momentum, and second law of Newton defines force as something that can change momentum. Third law of Newton is the most important out of 3, because in problem solving, whether or not you are able to understand a problem correctly depends on your understanding of the third law, which says that for every action there's an equal and opposite reaction. So an action-reaction pair of forces are formed, and their properties are that they have to be equal in magnitude. So the magnitude of action force that a body exists should be equal to the magnitude of the reaction force that the other object will exert back on it. they are also opposite in direction. So if action force is, for example, upwards, then the reaction force has to be vertically downwards. Third most important point is that they act simultaneously, that is at the same point, and they should act at the same time also. It does not mean that action force precedes the reaction or action force causes the reaction. Action reaction pair forces always exist at the same time, at the same point also. So this means that for any problem, whenever you have a action reaction force pair generated in your free body diagram, then you should keep in mind that the forces should act at the same point but on different objects, because their directions are opposite, and the forces will also have the same magnitude. These three properties of action reaction forces you need to understand very, very well. Only then will you be able to use the third law effectively while solving problems. Now, problem solving in this chapter, again, this chapter is entirely problem driven. So in order to make your approach very streamlined, you can follow this rough 5-step plan for solving problems in laws of motion. First of all, you should always draw free body diagrams of all objects in your system. Please ensure that every single force is accounted for, and whatever direction the force is, you are representing accurately in your diagram. Because if you make a mistake in the first step, then you will not even realize how many mistakes you are making in the subsequent steps. So drawing a free body diagram properly, taking into account each and every force that can possibly act on the object, mentioning the directions and the values clearly is very, very important. And also taking care of the fact that action reaction forces are acting on different objects but at the same point. Free body diagram is very, very important. Once you have drawn it, then you need to balance all the forces. Whenever any object is having a zero acceleration, then you should take the sum of all the forces, vector sum obviously, to be zero. But if the object is accelerating in a particular direction, then the net force in that particular direction should be equated to m into a. By this, you will get some equations of motion. And remember, our objective is to solve for whatever unknown quantities are asked in the question. And for that, we need at least n number of equations. We need at least as many equations as unknowns we have in the problem. And these equations are generated by either balancing forces or applying constraints of motion. Most probably, string constraints will be used, which we will take a look in just 2 minutes. Once you have equation of motions, then all you need is to solve them using appropriate techniques. The most common technique to solve is to eliminate the unknowns that you do not require. For example, if in a problem you have been asked the coefficient of restitution or you've been asked the acceleration, then you can write one quantity in terms of the other and substitute in the equations to eliminate those quantities. Alternatively, you can also use the method of adding and subtracting equations to reduce certain unwanted terms from the equations, hence eliminating unwanted quantities. But always, the method for solving any equations to get n number of unknowns is the only thing that you actually need to solve in the problem. Rest all is just following this particular recipe. And before marking the answer and moving on, it is very, very important to verify that your answers are correct or not. Again, if you make even a small mistake in the first step also, it will not be apparent how many steps this mistake is getting carried over in. So always keep in mind, keep verifying whatever steps you're doing, whatever calculations you're making, please keep verifying them as you go. So this 5-step plan you can roughly follow to solve any problem in laws of motion very, very quickly. Now the third point over here, that is applying string constraints, is very, very subtle but a very important aspect of problem solving. So let us spend some time understanding it. Not really understanding, but you should know what to keep in mind and what exactly a string constraint is. String constraint basically helps us, or any constraint of motion basically helps us relate the motion of one object with the motion of other object in terms of the actual kinematics. That is, the accelerations, the velocity, the displacement of two objects are related using string constraints. Constraints of motion. The basic constraints of motion are, for example, if there's an inclined plane and an object is sliding on an inclined plane, then the object is bound to move down the inclined path. That is also a constraint of motion, that the object should always have zero displacement, zero velocity, zero acceleration in a direction perpendicular to incline. That is also considered a constraint of motion. But the constraint of motion that will give you meaningful equations mostly will be string constraints in pulley problems. Different blocks will have different accelerations. And conceptually, if you want to remember, just you can remember this fact that in any system, if you have a block that has a tension T acting on it, like this one, and its acceleration is A, then acceleration of another block which has more tension acting on it will have less acceleration. If any constant C times the tension is the tension acting on another block, then its acceleration will be simply acceleration of the previous block upon the constant C. So higher the tension acting on the block, lower will be the acceleration with which it will move. But this will be useful to you if you can imagine that, for example, okay, if this block 1 is moving downwards, then this block 2 should move upwards. So direction of acceleration, if you can conceptually work out, then you can get its magnitude easily by this concept. But if you are not sure where the direction of acceleration of particular blocks will be, then also the technique is very simple. You can assume all accelerations to be in the downward direction. The maths will take care of itself. If the direction of motion of two objects are opposite, then the values of the acceleration will come out to be negative, signifying that the direction is opposite. But to assume, you can assume all the accelerations to be downwards. The maths will take care of itself and the values will be positive or negative depending on whether the acceleration is in your assumed direction or opposite to your assumed directions. But in this form, if you are assuming all the accelerations to be downwards, then the string constraint becomes also in a mathematical form, that for each block, the dot product of the tension force acting on it and the acceleration of the block should be constant. And if you take a sum over all the blocks in your system and multiply the scalar product for tension and acceleration, then all of their scalar products should sum out to be 0. And you should keep in mind that this constraint will give you exactly how the directions will also be related. So if the acceleration and tension are in opposite directions, the value of dot product will be negative. And if they're in the same direction, then their value will be positive. So you can assume any direction of acceleration. In that case, string constraint will be of a mathematical form. But if you can conceptually figure out the directions of blocks and they are correct, only then you can use the magnitude method. But just to avoid problems or any mistakes, the method of assuming directions always works. You will never make a mistake because you are trusting in the maths. Maths will take care of itself. If you are trusting your imagination to figure out the direction of acceleration, your imagination might sometimes make mistakes, but the maths will never make a mistake. Next, the concept of friction. You should keep in mind that friction always opposes a relative motion between two objects, but it is not always required that there has to be some non-zero or relative motion. Even if there is a tendency of relative motion, that is if an object is stationary with respect to some other object, but there is a force acting on it which will try to make it move in a particular direction, that is known as tendency of motion. Basically, force. If a force is acting, then there is something called static friction which will oppose the direction of the force, and it has an adaptive value if the active force that is causing tendency of motion is less than the value of coefficient of friction into the normal direction force at the surface, then the value of the static friction will adapt itself to the value of the force. But this adaptation only works until upper limit of magnitude of normal reaction force into the coefficient of friction. After the acting force exceeds this value, the value of static friction will be constant at mu into n. And as opposed to this, we have kinetic friction. When there is actually relative motion between two objects, kinetic friction will oppose that relative motion, and it has a constant value of coefficient of friction into the normal reaction force acting on the surface of the block. Again, the basic concept of friction, if you know, then you will always most of the time use the expression of mu into n anyway. Most problems do not have a separation in static and kinetic frictions. They are considered to be equal in the ideal cases. So just the form of the friction force you need to understand, and you can calculate the work done by friction, everything else, just simply using this form. Work and energy chapter, although it is a sort of complementary chapter to laws of motion, but the concepts are a little different. In work energy theorem, we will mostly use it in problems that involve motion between 2 points. That is, if you only have to compare the initial condition and the final condition of the motion of an object, you can apply work energy theorem that only works on initial and final points. There are 3 statements to the work energy theorem, and all 3 statements will be useful to you in some way or the other. However, the information they convey is the same, that energy is conserved in any motion, in any process. The first form of work energy theorem is useful in problems where you have a single object and you know all the forces acting on the object. So the theorem states that the total work done by all forces on objects is equal to the change in kinetic energy of it. And I have just split the work done for convenience, that is work done by conservative force, which you can easily calculate by integrating the force with respect to position. Work done by non-conservative force, the integration may not be very simple, because non-conservative forces are dependent on other quantities also. So I have separated work done by conservative forces, non-conservative forces, and any external force acting on your system will all add up, and that will be equal to the total change in kinetic energy of the objects in your system. The second form of work energy theorem is most widely used in problems. That is, for any motion of object, the total energy initially, that is the potential and kinetic energy, should be equal to the total energy finally after the object performs some kind of motion. This is the most widely used form of work energy theorem. So make sure that this form you are very comfortable with. The third form of the work energy theorem simply is conservation of energy in the mathematical sense. That is, the rate of change of energy is zero. Total energy of any object is constant with respect to time. This form comes into use in very particular and few situations, but when it comes useful, then you have a very big advantage. You can solve very complicated problems in just a few steps by using this form. Particularly in the chapter waves and SHM, this form has a lot more applications as compared to other chapters. So make sure you know all the 3 statements of work energy theorem, but you can use any statement, they all are equivalent. Over here we distinguish between conservative forces and non-conservative forces because of the way in which they do work on objects. Conservative forces are only dependent on the position. Non-conservative forces can depend on other quantities also, like velocity of an object, temperature of the surrounding or object, whatever. But the most important point is that for conservative forces, work done is independent of path taken, whereas it is dependent on the path for non-conservative forces. And if an object is traveling in a closed loop, for example, a circular motion, the work done by conservative forces is always zero at any time, because again, it is independent of path. Since the object has zero net displacement, there will be no work done. Also, we can say that force is a state function, so even work done will be a state function, not a path function. Now, when we extend our theory to multiple objects, earlier we were considering only point masses to be our objects, but if we have many different point masses together, or if we have extended objects, then we can assume that all the mass in our system is concentrated only on one point defined as the center of mass, which is basically the weighted average of all the positions of individual objects. Summation of the product of mass and positions upon the total mass in the system will be the center of mass. Similarly, this summation becomes integration in the case of extended objects. We assume mass element dm everywhere in the object and integrate it with respect to its position to get the center of mass of any extended object also. And center of mass, velocity and acceleration will also be the respective weighted sums of individual velocities and acceleration. So we can also calculate the motion of center of mass of our system and hence define the motion of all the objects in our system also. Now, using Newton's laws of motion for the entire system, we should have that the external force that we are acting on the system should be equal to the net motion of the system, that is simply the mass of the system into acceleration of its center of mass. This is the entire point. We are assuming that the entire object or any system of particles will be concentrated on one particular point, so that that one point follows our laws of motion that we have developed for point particles also. And just applying Newton's first law, if there is no external force acting on system, then the acceleration of center of mass will be zero. That is, the center of mass will have constant motion, and that just means that the momentum in the system will be conserved. The total momentum of all the objects in the system should be constant. This is simply the first law of Newton for a system of particles. Now, the most important part of this chapter, that is where 90% of questions you can expect from, is collisions. Now, the theory of collisions is very, very simple. All you need to remember is this one standard form of collisions where we have assumed all of the velocities of objects initially as well as finally to be in one direction. You will rarely have this kind of question. Most questions will have both the objects moving towards each other, not in the same direction. But the advantage of remembering a result like this is that even if you have been given both the objects to be moving towards each other, you can simply substitute the value of the velocity which is in the opposite direction to be negative. So if you have remembered these results and you have been given that mass m2 is moving towards mass m1, then you can simply substitute the value of u2 given to be negative minus of, if you've been given 10 meter per second square, then you will substitute minus 10 in terms of u2 and minus 10 over here as well. And depending on the value of v1 and v2 you get, if you get something to be positive, then you can be sure it's in the right direction. If you get something to be negative, it will be in the left direction. Very, very easy. So just keep in mind this one result and you will not have to remember anything else. All we are doing in collisions is that we are first conserving momentum if there is no external force acting during the collision itself. If there is any external force acting on both the objects, then that external force will do some work during collision and that will cause the system to gain energy. So the case when the collision actually has more energy after collision than before collision is the case in which there is some external force acting during collision. But if there is no external force, then we balance the momentum initially with the momentum finally of the system, and then we take into account any loss of energy that the collision might have had. And how we take into account is that we assume a fraction of the initial relative velocity, that is simply difference between two velocities. We know now relative velocity is simply the velocity of the object minus the velocity of the observer, in this case mass 2. So a fraction of the relative velocity will go into the final relative velocity. That is how we factor in the loss of energy, and this factor, called the coefficient of restitution, can take different values depending on just how much the loss of energy is. If there is no loss of energy, it is known as elastic collision and the value of E is 1. All of the relative velocity initially will go into the relative velocity finally. There will be no loss of energy in the system. If there is some loss of energy, then the value of E will be less than 1. That means the final relative velocity will be less than the initial relative velocity. For the condition where E equal to 0, there will be a maximum loss of energy, in which case the relative velocity itself will be equal to 0, or both the objects will stick together and move with the same velocity after the collision. This is known as perfectly inelastic collision. Perfectly inelastic because it has the maximum loss of energy possible, and there is zero relative velocity between the blocks after collision. So in this case, where we have perfectly elastic collisions, we will simply be able to solve for collisions using conservation of momentum. We won't even have to go into factoring loss of energy itself. So just remember this one result, and everything else you can simply derive from this one. Now the next chapter is rotation. Now this looks like the most difficult chapter in your entire syllabus. Very tough questions can be asked from this chapter, and most students struggle the most with this chapter itself. But the fundamental thing you need to remember is that whatever theory of motion we have studied in the previous chapters, laws of motion and work power energy, we will be applying the same principles, the same theory, but instead of a motion in one dimensions where objects are actually moving, we will consider objects that are rotating about some axis. So the quantities that we have defined for motion, that is momentum and force, we will define in terms of angular motion, that is angular momentum and angular force, which is called torque also. And in order to convert from linear quantities to angular quantities, all we need to do is cross product with the position vector of any object that is required to us. For example, the angular momentum is simply position vector cross product with the linear momentum at that particular point will give us the angular momentum, and similarly cross product of the position vector with the force will give us the angular force or the torque. And over here the inertia of the system is also defined with respect to rotation, that is angular momentum, angular inertia we call as moment of inertia, and it's also a very simple integration to calculate the moment of inertia about any axis. Now this integration may not be very straightforward, and in some cases the integration may not be even possible. So we use axis theorems to calculate the moment of inertia about any axis. Parallel axis theorems and perpendicular axis theorem states that if you have any two-dimensional object and you have an axis perpendicular to it passing through the center of mass of the object, this is known as a standard moment of inertia, or a standard axis which passes through center of mass and is perpendicular to the plane of the object. Parallel axis theorem states that if you have any axis parallel to the standard axis, then the moment of inertia of rotation about that axis simply becomes the sum of the standard moment of inertia and md square, where m is the mass of the object and d is the parallel separation between the two axes. Similarly, perpendicular theorem states that for a two-dimensional object, there will be two perpendicular axes in the plane of the object and one axis perpendicular to the plane itself. The moment of inertia about any of these three axes can be related as the moment of inertia of the perpendicular axis is equal to simply sum of moment of inertias of the two axes in the plane of the object. Remembering these theorems might simplify your calculation of moment of inertia very much. You might find that calculating the moment of inertia about some axis, let's say any axis, is a very complex integral, but splitting the terms into a standard axis might be easier to calculate, and simply using parallel axis theorem you will be able to simplify your calculations, maybe from 4 to 5 steps to a single step calculation also it is possible. And you also need to remember the standard values of moment of inertias for different geometric shapes. If you remember the results, then you can solve problems very quickly. Otherwise you can derive any geometric shape you want. It is not really difficult. And energy is also defined similarly. Rotation, we treat it as another form of motion or a degree of freedom, so to say, and the kinetic energy associated with rotation simply is half into inertia into velocity square. And the case of rotation plus translation, if the axis is itself moving in some velocity, then we will add the total kinetic energy of translation with the rotational kinetic energy in order to get the total energy of the rotating and translating system. And a special case of it is known as rolling motion, where the velocity of axis is exactly equal to radius of object into the velocity, angular velocity of rotation about that axis. Again, people take this concept very seriously, way too seriously. In fact, it is very easy. All you have to do is apply this condition for the velocity of axis and the angular velocity, and everything else will be exactly the same as the procedure that we looked at for problem solving in laws of motion. Just instead of a force diagram, you will draw a torque diagram. Instead of equating force to mass into acceleration, you will equate torque to moment of inertia into angular acceleration. Everything else, getting the equations of motion, solving them for any number of unknowns, will have the same general plan as we have seen for laws of motion. Now the next topic, simple harmonic motion, it is actually a very simple topic if you can remember just this one result, that acceleration of an object undergoing SHM is equal to minus of omega square into x. You always have to simply write down the restoring force on the object and get it into a form where restoring force is proportional to the displacement of the object from mean position. In this case, you can equate F equal to ma and get the acceleration equation. Remember, when you write down the acceleration of object, whatever is sandwiched between the minus sign and the variable x becomes your angular frequency omega, and you can also calculate the time period, which is required in 90% of questions. You will be asked to find the time period of a particular SHM. Procedure is very straightforward. Write down the restoring force, try to get it proportional to x, use this form a equal to minus omega square x, write down the angular frequency and simply calculate the time period. Superposition of SHM is the most important topic over here, but we can even simplify that calculation by assuming the amplitudes to be vectors. This is also known as phasor method, where amplitude of each individual SHM is considered to be a vector and the phase difference is considered to be the angle between the two vectors. Just like parallelogram law, we can add the net amplitude using vector addition, and also the phase of the resulting SHM can also be obtained by the expression for angle of the resultant. Again, parallelogram law, we apply exactly the same. And using a phasor method, we can also calculate how to superimpose two simple harmonic motions if they are not on the same axis. If they are on perpendicular axis, that is x and y axis, the overall motion of the object will also be a two-dimensional motion, which will have some x component that behaves like this and some y component that behaves like this. Some special cases of such a two-dimensional motion are sketched in front of you. These are known as Lissajous curves or Lissajous figures. You only need to remember the conceptual behavior of the object, how exactly it performs motion. For example, if there is no phase difference between the two individual motions, then the object will perform simple harmonic motion along some diagonal line. If there is a phase difference of pi by 2, it will perform a uniform speed motion on this ellipse. That is the only thing you need to keep in mind, the two-dimensional behavior of the object. Simply these three cases are the only ones that are required. The rest of the maths becomes a little bit more complicated and you will need a strong knowledge of conic sections to solve questions otherwise. Damped harmonic motion is also very simple because we consider only one special case in which the damping force is proportional to velocity, just like the restoring force was proportional to displacement. And in this case, the solution becomes very easy. You get a time-dependent amplitude, that is an amplitude that constantly decreases, and your object performs simple harmonic oscillations with that particular time period at every instant of time. And the formula for angular frequency directly will be used if at all you get a question from this part of the topic. Waves is the obvious extension of simple harmonic motion because waves are formed in a string, and in a string every individual particle, if it performs a simple harmonic motion with varying phase as given by the distance but with the same time period, then we'll observe that the point that has the maximum displacement at any time, it will seem to move towards the right or the x-axis, but there is no motion actually happening on the x-axis. The only motion that happens is that particles perform simple harmonic motion in the y direction. That is the real motion over here. But we observe that the position of the maximum amplitude particle slowly shifts towards the right. That is only the apparent motion. There is no real motion happening in the x direction. You need to remember the formula for velocity of waves in a string, the relation of frequency and lambda with the speed. This is very, very important. This will be used in subsequent topics related to waves also. And you need to be able to read how exactly the wave equation represents the actual wave. If you just remember this much, then you will be able to easily apply this in any problem given to you. Superposition of waves also follows a similar pattern. We consider amplitudes to be vectors and add them using parallelogram law. In this case, we will get a condition for maximum amplitude for a particular value of phase difference. The conditions for maxima and minima also will be consistent in subsequent chapters involving waves also. So keep in mind that you have understood and you remember the conditions for maximum amplitude as well as minimum amplitude, which gives us constructive and destructive interference respectively. And a feature of traveling waves is that if you have two waves moving in the opposite direction with the same amplitude and same frequency, they combine to form something known as standing wave, in which the phase of oscillation is the same for each and every particle on string, but there is a position dependence on the amplitude of simple harmonic motion, A sine omega t. The amplitude is changing with the position of the particle in the x-axis. So the entire string will oscillate in phase, but we'll observe that some particles have a higher amplitude than the other particles. The particles with zero amplitude that will not even oscillate are known as nodes, and the particles with maximum amplitude are known as antinodes. And depending on how many nodes and antinodes you have, what we get are called harmonics on a string. Harmonics basically tell us what mode of vibration the string is executing. For example, if there is one antinode in a string closed at both ends, then we call it as the second harmonic or the first overtone. And if there is no antinode in between the string, then for a free end of the string, it is known as the fundamental mode of oscillation. And a point to note over here is that the case in which both the ends of string is fixed is the same as that for a resonance tube in which both the ends are open, and vice versa. We get exactly the same expression for the length versus the wavelength of standing waves for a string also and for sound waves also. So you only need to remember these two conditions and you will be able to apply exactly the same concepts for sound waves also in a resonance tube. Doppler effect is a very, very important thing to understand because questions can be very, very easily framed from this, and it is very easy to memorize also. Again, you can consider a simple case in which all of the objects, source as well as detector, is moving towards the positive x-axis, and if you have any object moving in the opposite direction, you can simply substitute the value of its velocity as negative and exactly the formula will not change. If you are not able to remember this formula, you need to keep in mind just two things: that if the separation of the source and detector is decreasing, then frequency observed should increase, and if the separation is increasing, then frequency observed should be decreased. And the source velocity always comes in denominator and the detector velocity always comes in the numerator. So for example, if the detector is moving away from the source, it will try to decrease the frequency, and hence the numerator should become smaller, hence we get minus of Vd. And if the source is moving towards the detector, then separation will be decreasing, and hence this motion will try to increase the frequency, hence the denominator should be smaller and we will get minus of velocity of source in the denominator. Again, if you can remember this formula as it is, very, very good. If you can't, remember just these two concepts and the fact that detector speed is always in the numerator and source speed is always in the denominator. That is it for the waves chapter. Now the next chapter is properties of matter. That is, we need to define the properties of solid, liquids and gases depending on the theory of motion that we have already established in the previous chapters. When it comes to solids, the only property important and relevant to your syllabus is elasticity, wherein if we disturb any solid object, it tries to restore itself back to its natural state. And Hooke's law states that the stress that will be induced in this object, which is basically the restoring force per unit cross-section area of the object, will be proportional to the strain, that is the fractional change in the dimensions of object that we cause by disturbing it will be the strain, and the proportionality constant is known as modulus of elasticity. But one thing to keep in mind is that Hooke's law is only valid if the strain we induce in the object is very small. That is, we don't disturb the object too far from its natural state. If this assumption is broken, then what happens we'll see in a minute. But Hooke's law gives us the relation between the exerted restoring force that is responsible for bringing the object back to its natural state with the amount by which we had disturbed the object, and the energy density stored as a result of this disturbance can simply be written as half into stress into strain, with the total energy obtained just simply by multiplying with volume. So just remembering these two simple concepts, you will be able to solve any single problem from elasticity. Remember, depending on the kind of strain that we are exerting, the modulus of elasticity will also be different. Young's modulus for linear expansion, shear modulus for areal disturbance, and bulk modulus for volumetric expansion or contraction will have different values. And if the assumption for Hooke's law, that is the strain is very small, is broken, then the behavior of stress with strain can be detailed using such a curve. We know that for small values of strain, Hooke's law is obeyed. Hence, the stress will be proportional to strain. This is known as proportionality limit, where strain is simply proportional to the stress. Beyond this, the additional amount of stress that is produced will gradually decrease, and there will come a point beyond which the object will no longer be elastic. It will not be able to retain its natural position after deforming it. There will be some permanent deformation in the object once we deform it over the yield point. Yield point is the final point where the object behaves elastically. Beyond the yield point, the behavior of object is plastic, that it will not return to the natural state after deforming. And beyond the fracture point, if we keep deforming the object, then the object will break, because the intermolecular interactions themselves will not be able to keep up with the required restoring force to keep the object intact. This is a very simple curve. Mostly conceptual questions are asked on this curve. Mathematical questions can only be asked about the yield point, which is simply the inflection point on the curve. Before this inflection point, object behaves elastically. After the inflection point, object behaves plastically. That is literally it for solids. In liquids, the phenomena we observe is that the surface of liquids behaves differently as compared to the bulk of liquids, and as a result, there is some extra force acting everywhere on the surface of fluids, which is known as surface tension. And the surface energy is also related to surface tension as simply the surface tension into area. Just these two expressions, if you keep in mind, you will be able to derive every single result from this chapter. The only result that are important is the excess pressure inside liquid drops and bubbles. Again, just remember this format. For a soap bubble, you only need to replace the surface tension with twice the amount of surface tension, because a soap has 2 layers of surfaces. So surface tension will be exactly doubled in the case of a soap film, and simply replacing S by 2S, we get all the results for soap films as we have obtained for liquid surfaces also. And liquids also show capillary action as a result of their meniscus. If a liquid has lower meniscus, then there will be a capillary rise. If a liquid has upper meniscus, there will be a capillary depression. And this can be summarized using only one formula for capillary action, that is, the height will be 2s cos theta, where theta is the contact angle with the walls of capillary, upon rho g r, where r is the radius of the capillary. We can clearly see if the liquid has a lower meniscus and theta is acute, cos theta will be positive, and hence there will be an increase in height. If the contact angle is an obtuse angle, for upper meniscus, cos theta will be negative, and the value of h will also be negative, telling us that there is a depression in level of the fluid. And liquids also exert two forces, resistive forces. They exert viscosity on each other's layers, and just the form of viscous force you need to keep in mind. It depends on the velocity gradient. And drag force is acted on any spherical object that is moving inside a stationary fluid with a constant velocity. Again, Stokes' law is an approximate limit of the drag force. And again, if you remember just the form of drag force, you will be able to solve pretty much every question that you can be asked about this. And fluid mechanics has only two equations really: equation of continuity equation and Bernoulli's equation. Continuity equation is a result of conservation of matter, and Bernoulli's equation is a result of conservation of energy. If you just remember these two facts and the expressions of these two equations, that is A into V is constant for equation of continuity, and the total energy density terms are constant for every point in a flowing fluid. If you simply keep in mind these two equations, every single question, every single result can simply be derived from these two expressions themselves. And the only result you need to keep in mind other than this is the velocity of efflux, which depends on the area of the orifice that we are opening and the level of water above the orifice. But if the area is very, very small, then the velocity takes a very, very simple form, root of 2gh. These are the only two results you need to remember from fluid mechanics, and just applying these results you will be able to solve most of the problems also. For gases also, you have learned kinetic theory of gases a little bit in chemistry also. Ideal gas equation PV equal to nRT. Just the additional quantity in physics is we are no longer bothered about the number of moles. We might be interested in the total number of particles in the gas sample also. They are simply related by Avogadro's number. Hence, their equations will also differ by the constant, which is also related by the Avogadro's number. Just the simple form PV equal to nRT, if you remember, which I don't think anyone can ever forget PV equal to nRT in their life. Just like mitochondria is the powerhouse of the cell. One thing I remember from biology, one thing I remember from gases is that PV equal to nRT. After that, you need to only remember in kinetic theory how the RMS speed of gas varies and the variation of average kinetic energy and the average pressure of a gas. Because the entire point of kinetic theory of gases was to study the properties of gases like pressure, temperature, etc. with their kinetic properties of molecules. Using the motion of molecules, we had to explain the pressure. Using the motion of molecules, we had to explain the temperature, so on and so forth. So these are the only three results that you need to remember from this chapter. And real gases also have very, very simple behavior, just a little bit more complicated than PV equal to nRT. You have to take into account the corrections due to intermolecular attraction and the correction due to molecular size of real gases, if you can keep in mind. Then van der Waals equation also should not be a very big deal to memorize. Keep in mind that it's just PV equal to nRT, but we are making slight corrections on pressure and slight corrections on volume respectively. Everything else is the same. And equipartition theorem simply states that energy is no longer due to only motion. There are other degrees of freedom also available for real gases to store energy, like rotation, vibration, etc. But doesn't matter, the number of degrees of freedom is equal to thrice the atomicity. So for example, if you have a diatomic molecule like oxygen, there are two atoms, so the number of degrees of freedom will be 3 into 2, that is 6. But these degrees of freedom are taken into account the vibrational modes also. For low temperatures, that is temperatures below 100 degrees, probably not 100 degrees, but for generally room temperatures, we do not consider the vibrational degrees of freedom. So be sure to keep in mind in chemistry, sometimes the vibrational degrees of freedom might be neglected, but doesn't matter. Energy stored per degree of freedom will always be half into kT, and based on the number of degrees of freedom you have, the total energy of gas will be number of moles into number of degrees of freedom into energy per degree of freedom per mole. Very, very simple topic. Just remember the fact that energy is stored per degree of freedom and you will be able to do the rest easily. In thermodynamics, with the chapter is divided into 3 units: calorimetry, thermodynamics process, and then heat transfer. In calorimetry, we basically keep a track of any heat exchange between two objects. A hot object will provide heat to a cold object. So unless we have any loss of energy in the surroundings, the total heat lost by the hot object should be equal to total heat gained by the cold object. That is the principle of calorimetry. And we can calculate the heat loss and heat gained by these basic elements. The energy required to raise temperature of any object is defined in terms of the specific heat. For solids, this specific heat is known as the heat required to raise temperature of 1 unit mass of any object with some time temperature delta T. For gases, we cannot measure the mass of gases accurately. So instead, we use number of moles to note the quantity of gas, and specific heat is defined in terms of molar specific heat. That's the only difference. Everything else is the same. And when there is no change in temperature, but heat is instead utilized in phase change, that is changing from liquid to gas, solid to liquid, so on and so forth, the energy required is known as latent heat, and it is the energy required to change the state of 1 unit mass of object. So total heat required is the mass into the latent heat of that particular object. Using these three elements, we can calculate and equate the energies lost and gained. The chapter, the topic is over. Only specific heat and latent heat is what you need to keep in mind in this chapter. For thermodynamic process, the only thing you need to care about is the first law of thermodynamics. That is, the net change in internal energy of a system is equal to the heat provided to a system minus the work done by the system. Because we are defining work done by the system, work done will result in a loss of energy of the system. So the energy of system will decrease if it does work. That is why the first law is stated as such. And if you know the results for the work done, the heat provided, and change in energy for these four standard processes, if you can memorize the expressions for these quantities, then problems will be very, very simple for you. Otherwise, you will have to sit and derive all these quantities for every expression. It looks like there is a lot to remember over here, but if you remember it logically, that is, the change in internal energy is always NCV delta T. And for a constant pressure process, isobaric, the heat capacity is the heat capacity at constant pressure, which we already know from the atomicity of the gas. And since the temperature is constant in isothermal process, we can simply start writing nRT, and then log V2I1 just will come naturally once you solve enough problems. Again, if you can keep in mind these results, your time taken to solve questions will be greatly reduced as opposed to sitting and deriving them for every problem. The second law of thermodynamics is not really important, but just the application of second law, that is heat engines, is important, because questions can come directly from heat engines. They will give you the temperatures at which the engines operate, and you might have to find the work done by the engine, so on and so forth. All you need to remember is that the efficiency is defined as the useful work done upon the total heat supplied. If the engine absorbs heat Q1 and releases heat Q2, the work done will be Q1 minus Q2, and the heat supplied is exactly Q1. For a Carnot cycle, which operates between two temperatures T1 and T2, this efficiency is always equal to 1 minus the cold temperature upon the hot temperature. And you can relate this with the expression for efficiency and calculate the heat provided or the work done or the heat released, whatever it is, you can calculate by simply using these two expressions. That is all you need to know about heat engines. Heat transfer, you only have conduction and radiation in your syllabus. In conduction, we consider heat to be traveling in one dimension between 2 points at a temperature difference of delta T. We can write the heat current, that is the amount of heat flowing per unit time, will be proportional to area, inversely proportional to the distance over which it has to travel, and will be proportional to the temperature difference between 2 points. You can compare this to electric current, that the current is equal to potential difference upon a resistance. Whatever is divided by delta T will be the thermal resistance, which you can easily write. Here we define conductance or conductivity of the particular substance, and you can write the heat current with the temperature gradient. If the temperature is dropping smoothly, then the value of temperature gradient at any point will give you the heat current flowing through that particular point. Radiation is also very, very simple. All you need to remember is Stephen Boltzmann's law, that is the power radiated by black body is proportional to fourth power of its temperature. And this energy radiated in terms of electromagnetic waves is radiated in all wavelengths, but only one wavelength will have maximum energy dedicated to it, and that can be calculated using Wien's law. Wien's constant is very, very simple. Wien's law just states that the maximum energy wavelength will be inversely proportional to temperature of the object. So the power radiated, total power radiated is proportional to T power 4, and the wavelength will maximum energy is proportional to 1 upon T. These are the only two things you need to keep in mind in radiation. And because of this, objects kept in environments, in cooler environments, will start to cool by losing heat, and the rate of cooling is defined in Newton's law of cooling as proportional to the temperature difference between the object and surroundings, but only if object and surroundings are very, very near to each other. There is no drastic jump in temperature from surrounding to object. If the difference between temperatures is, I would say, less than 10 times of the individual temperature of object or surroundings, then Newton's law of cooling holds. But again, it is an approximate law, and you don't need to actually integrate temperature with time in all the questions. If the temperature is continuously changing, you can also take the temperature of object to be the average temperature and simply write Newton's law of cooling for every process. Now, the next chapter starts the 12th standard syllabus with electrostatic, and I believe chapters from 12th syllabus are easier than chapters from 11th syllabus, because in the 11th standard chapters you need to have a conceptual understanding of every chapter, and also you need exposure to diverse range of problems in order to easily solve most problems. But in 12th standard chapters, if you simply remember a few key concepts from every chapter, almost all the questions involve just direct application of those concepts, some formulas, some equations, some result directly applied will give you very, very easily the answer to any problem. Let's start with electrostatics. In electrostatics also, you need to remember just these four basic things. Coulomb's law gives you the force between 2 point charges. You can integrate this in the differential form to get the force between any two extended charges also. The definition of electric field and electric potential is very, very simple. Electric field is the force per unit charge. Electric potential is the potential energy per unit charge. And for symmetric systems, we can use Gauss law to calculate the electric field at any point on a Gaussian surface, which will be proportional to the total charge contained inside the Gaussian surface. Every single thing from this chapter can simply be derived from just these four concepts. So again, remember these four things, and with enough practice, every single question can be solved just using these. Now, the only thing other than these four concepts you need to remember is the concept of dipoles, which have charge distribution within one particular object. Some positive charge and some negative charge will be separated by distance of d, and we can represent this system with a single quantity known as dipole moment, which is defined in this way. For this, you can calculate the electric field at any point, the potential at any point due to these two charges, just by using Coulomb's law and the definition of potential easily. But the two important values you need to keep in mind is the electric field on any equatorial point and the electric field on any axial point far away from the dipole. These two values of electric field, if you keep in mind, then many questions have direct application of this formula as well. And the most important thing is that any dipole in an electric field will experience some torque, and this torque you can write as the cross product of dipole moment and electric field. And for small angle theta between the dipole and electric field, since the torque is coming out to be proportional to the angular displacement, we know it will perform simple harmonic motion around an equilibrium position. It's a very, very favorite topic and has been asked in every exam ever. Either electric dipole or magnetic dipole oscillating in a uniform field. It's very, very simple. All you need to keep in mind is that the torque is cross product of dipole moment and the electric field. Capacitors are simply extension of electrostatics. That is, if you have a system of two conductors conducting plates, then the charge stored in this system will be defined as the capacitance, which is a property of the system itself, and the voltage or the potential difference applied across its ends. And The energy is also defined as half into C into V square. Simply, we define a constant C, which is the called capacitance for every system. And depending on the value of capacitance and the voltage applied, there will be some charge stored in the system. The value of capacitance for a parallel plate also has a very, very simple formula. And if you remember at least one other result, that is the capacitance for a spherical capacitor, or let's say a cylindrical capacitor, you can derive these on the spot also. But if you remember values, then again, questions will take much less time because you'll be able to remember very, very quickly. Usage of capacitance circuits is important because most questions from capacitors will be connected either to current electricity or alternating current or electromagnetic induction, something like that. So you need to know how capacitors are used in circuits. If we connect capacitors in series, the charge stored in between them will be equal and their equivalent capacitance will follow a harmonic sum. Versus if we connect them in parallel, the charge stored will be different for both the capacitors, but the voltage difference across them will be the same, and the equivalent capacitance of the system is simply addition of both of their individual capacitances. Current chapter is also important because questions can be related to other chapters also. All you need to keep in mind is that for a general conductor with general charges flowing with some drift speed, we define the current as the number density of charges into charge on each particle and the drift speed of charges. Now we also define a vector quantity called current density, which is the current per unit area in the conductor, and the general form of Ohm's law states that current density is proportional to induced electric field. That is, if we are applying an external electric field onto a conductor, we know the charges will start moving and then a current will be established. But the inverse is also true according to Ohm's law. That is, if we have some current density inside of a conductor, those moving charges will also create an electric field like such. This, if you understand this concept, then the concept of depletion layer in semiconductors, PN junction, will also be clear to you. And for ohmic resistors, that is for ideal conductors, this phrasing of Ohm's law reduces to the famous expression current is equal to applied potential difference upon the resistance of the conductor. Now, Kirchhoff's laws are important to solve circuit questions. We only have two, Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law basically says that the charge is conserved at any point in the circuit. So the net amount of current flowing into a particular point should always be equal to the net current flowing out of a particular point. I think I missed the direction of I4 over here, but it's fine. You get the logic, right? The total current going in should be equal to total current going out. This expression should have minus I4, I guess. And for voltage law, it is just the arithmetic addition of the voltage drops across all the components in any branch will give us the potential difference across branches. And in the case of closed loops, the sum of potential drops across every component in that loop should be equal to 0 because we are starting and ending at the same point in the circuit. So there should be no potential difference between a point and itself by definition. And the concept of Wheatstone bridge is important because if you just are able to see this pattern, then many problems can be simplified such that the calculation is very easy as you expected. Bridge is basically any resistor that is connected perpendicular to the flow of current. So you can imagine that the current is some river and you are constructing a bridge to cross the river. Bridge always goes from one bank of the river to another bank of the river perpendicular to it. So any resistor connected across the direction of current is known as a bridge resistor. And on the either side of the bridge, if the ratio of resistors connected is the same, that is for this particular bank, the ratio R1 is to R2 is the same as for this particular bank, ratio R4 is to R3. If these ratios are the same, then we observe symmetry in the circuit. That is, the current coming in should be the current going out. So the current will split exactly the same and it will again recombine to form the same amount of current. It will be as if there is no current flowing through the capacitor, the resistor R5, and R5 is disconnected from the circuit. That is all for the current chapter. In the next chapter, magnetism, you should see that we are approaching the topic in the same way as we approach electrostatics. There'll be some electric field over here. There is magnetic field. There was some electric potential. Magnetic potential does not exist because magnetic force is a non-conservative force. Keep in mind, potential is only defined for conservative forces. And we know that for any charge moving with some speed v inside a magnetic field, the magnetic force applied on it is the cross product of its velocity and magnetic field. Similarly, for a current carrying wire, we define charge into velocity as current into length, and the other expression is the same. Just like electric dipoles, a current carrying loop of wire forms a magnetic dipole which has a magnetic moment given by the current into the area of the loop. And similar to electric dipoles, it will also experience a torque in the perpendicular direction if we place it in a uniform magnetic field. This is the only two results you need to remember, the torque result and the force result. If you can remember results for a cyclotron, that is a charged particle moving in a circle inside a magnetic field, then problems will be very, very easy. But these can easily be derived simply from this equation, as we can see over here. If the velocity is perpendicular magnetic field, the force will simply be Q into VB. We can equate this to required centripetal force mv square by r and easily get the value of cyclotron radius. Similarly, we can derive cyclotron frequency also, and the time period of oscillation of a cyclotron can also be derived in a similar way. In magnetism, we also need to calculate the magnetic fields due to different current carrying wires. Biot-Savart's law, you need to keep in mind in its differential form, and in a simplified form for a straight wire, Biot-Savart's law in terms of sines of apex angles, you need to keep in mind. And as the counterpart to Gauss law in electrostatics, we have Ampere's law. For every current, we can draw any closed loop around the current, and the magnetic field at that loop will be given by Ampere's law. It will be proportional to a total current enclosed inside the closed loop known as Amperean loop. Again, compare this with Coulomb's law and Gauss law respectively, and you can see a pattern of similarity between the two chapters. For electromagnetic induction, you need to keep in mind that the magnetic flux related to any current carrying loop will generate an EMF in between if the flux is changing. And Faraday-Lenz law states that the resultant flux is equal to negative of rate of change of magnetic flux. The minus sign is there to denote the fact that induced EMF always opposes the cause that causes it. So if the magnetic flux is getting increased, EMF will try to decrease it, and vice versa. If the magnetic flux is changing due to some motion of object, it is known as motional EMF. And for any kind of situation in which any motion of some form leads to some EMF, the EMF will always get reduced to such a form. EMF always equals B into L into V for motion generating EMF. And using this simple form of Faraday-Lenz law, you can even derive quantities like self-induction. All we do is we assume that the flux is proportional to the current, putting a proportionality constant self-inductance, we can write the magnetic field due to any coil, and the induced flux will depend on this particular value of the coil. Again, you can derive this simply using this one equation. This is the only thing you need to remember from this chapter. Everything else is just application of it. In alternating current also, the problems can be simplified very, very much if you remember the forms of current for various circuits and the fact that for power dissipation, we need the root mean square value of current, which we define as the amplitude of current upon root 2. For simple circuits, that is alternating current sources being connected to a single circuit component, different components will give us a different form of the current. Some will, in for example capacitor, it causes the current to lead the voltage by pi by 2 phase, and inductor causes the current to lag the voltage by pi by 2. And the term that works like resistance in all of these current sources is known as the reactance for each component, and that we can assume as the equivalent resistance to alternate current that all of these components provide. Even if we have a complicated circuit where we are combining more than one components, we can use phasor method to solve them. Simply write the equivalent resistance due to each component along with the phase that they differ from the voltage. Capacitor makes the current lead by 90 degrees, so the angle between capacitor and horizontal will be 90 degrees, and a resistor current is in phase with voltage, so it will be a horizontal vector. And we can add these two effective resistances or reactances vectorially to get the final impedance, which is simply the effective resistance of the entire circuit. So by vector addition, we can get the amplitude of current also and the phase also, and then writing current as I naught sine omega t plus phi, we'll be able to exactly write down the current flowing in the circuit at any point in time. Now, electromagnetic waves is the least important chapter in the syllabus, I would say, because there have hardly been any questions in the last 10 years or even 20 years. I have no idea. But if you keep in mind just three basic properties of electromagnetic waves, the fact that the amplitudes or the plane of oscillation of these waves is always perpendicular to direction of travel, the fact that the amplitude of electric field is always equal to speed of light times the amplitude of magnetic field, and the value of the speed of light in terms of fundamental constants of nature. 90% of questions will be conceptual questions and based on just these three properties of electromagnetic waves. This is a very, very small chapter, and if you can remember energy density and Poynting vector, then a few more questions will be easier for you. But again, hardly a question will be asked from this topic. Just to play it safe, remember the properties of electromagnetic waves in case a question is asked. For ray optics, you need to remember a large number of results, and if you have those results by heart, then you will not face any difficulty in solving problems. Only if you don't have any results by heart, you will find it difficult to logically approach a question. So if you have the results, if you remember Snell's law, if you remember the refraction from plane surface, if you remember the law of refraction for refraction from a spherical surface into a medium, then you can apply any of these to calculate the law of refraction for lenses, for example, law of reflection for mirrors, for example. But again, if you can remember the results for lens formula and mirror formula and also lens maker formula, then you will not have difficulty in 90% of problems at all. 90% of problems in ray optics are from just these three topics: mirrors, lenses, and refraction from spherical surfaces. These three topics are responsible for 90% of the questions in ray optics. So make sure that you clearly have three formulas at least by heart, and if you have the lens maker formula also by heart, then 95% of questions will be very, very easy from you in ray optics. In wave optics, you need to know the basics of Eisen's principle, that is the theory of wavefronts, wavelets, and the fact that light rays are perpendicular to every wavefront. You need to understand these quantities, but mathematically questions can be asked about the variation of light with the distance traveled. Remember, according to Eisen's principle, the intensity of light varies inversely proportional to the square distance traveled by light. So as light travels greater and greater distances, its intensity will rapidly decrease. That is why we have difficulty looking at light that is coming from a greater distance, because its intensity has been reduced a lot in traveling that particular distance. And you need to know that the path taken by light depends on the medium in which light travels. If light is traveling in air, then yes, the physical distance traveled by light will be equal to the optical distance also. But if light travels through any medium of refractive index mu and thickness d, then because of the density of this medium, the optical density of this medium, light seems to travel an extra path mu minus 1 into d because of the slab of refractive index mu. You will need to apply these concepts to solve questions from double slit experiment, diffraction, etc. Again, for simple condition of double slit experiment and diffraction, you need to keep in mind the conditions for maxima and minima. If you are given non-trivial problems, that is, let's say the setup is immersed in water, or only half the setup is immersed in water, or let's say a glass slab is kept in front of some source, or let's say there's only one source and a mirror which reflects and causes interference. In any case, there will be some form of two sources of light, and you will need to calculate the path difference between the two sources, equate it to any multiple of lambda to get constructive interference, or any half multiple of lambda to get destructive interference. And for diffraction, it's the exact opposite. If you compare b sine theta to d sine theta, in both cases, the condition for maxima is similar to condition for minima over here, and the condition of minima for diffraction is similar to the condition for maxima over here. So just this difference you need to note. For diffraction, the expression for maxima and minima is reversed as compared to for a double slit experiment. Now the only concept remaining in wave optics is polarization, and you only have to remember one law known as Malu's law, and the fact that if you polarize an unpolarized light, the intensity reduces to half, and if you change the polarization of light, then the outgoing intensity is equal to cos square of the angle between them times the incoming intensity. This is the only thing to remember. Almost all questions on polarization are either conceptual, or just need to use Malu's law. In modern physics, again, there are 4 topics, and you need to remember just one key point from every topic. The key point from dual nature you need to remember is photoelectric equation and the de Broglie wavelength. Again, you have done this in chemistry also and in physics also. So you can remember one concept from chemistry and one concept from physics. So in total, you only have one thing to remember from both subjects, because chemistry and physics have both of these concepts common in the syllabus. In the case of atomic structure, again, everything is exactly the same as you have learnt in chemistry. The most likely question to be asked might be related to the absorption or emission spectra. You need to keep in mind the energy levels of electrons in a Bohr model vary inversely proportional to n square, and you can then use this relation to calculate the energy difference between orbits, and hence the energy of photon that needs to be absorbed to excite or will be released on de-excitation. When it comes to radiation, you only need to remember the law of radioactivity. You need not even remember the final result for simple decay, because if the system is not simple, if your system is a slight bit complicated too, like for example, you are allowing a sample to decay, but you are also periodically supplying the sample with nuclei from your side. In that case, you will write the rate of decay is the proportionality with the number of nuclei, and you will also add some nuclei with some time dt. So yeah, if you just remember the rate of decay is proportional to the number of nuclei at that particular point, then nothing else you need to keep in mind. Simply solving this one equation all the time will give you the correct answers. And this is a first order kinetic process. So if you remember chemical kinetics, then you can apply any result that you will know for first order reactions to nuclear decay also. This allows us to observe the nucleus of atoms, and the first result that we have in this chapter is the fact that mass of nucleus is not equal to the total mass of its constituent particles, and the difference in the masses of its constituent particles with the observed mass of nucleus will give us the binding energy, that is the energy that is required to keep this system stable. And using this fact, you can calculate the energy of any nuclear reaction simply as the difference in binding energies of products and reactants. And the kind of nuclear processes that you need to know from this chapter are only 3 processes: alpha decay, beta decay, and gamma decay. You need to know how the atomic number and mass number of nuclei changes for different kinds of reactions, and the fact that the nucleon number is conserved for all nuclear reaction. Number of protons may not be conserved, although it is mostly conserved, but the number of nucleons, mass number, will always be conserved in every nuclear reaction. And the last topic is semiconductors. Again, not a very important topic, because most of this chapter is very concept heavy, and it depends on how much you have understood this chapter when you first learned it, because you can't really understand or build a strong foundation of the chapter at this point. But to solve problems accurately, you need to keep in mind a few things. The definition of semiconductor can be asked in the form of a conceptual question. The band theory of valence band and conduction band, and the fact that current can only be carried if there are charges in the conduction band, either by kinetic excitation or by thermal excitation, then this object will conduct electricity. And depending on the type of charge carriers present in our system, we can classify semiconductors into N-type and P-type. N-type semiconductors have electrons as the major charge carriers, and P-type semiconductors have holes, or the positively charged particles, as the primary charge carriers, and they should doped with pentavalent impurities, that is electron rich impurities, are required by N-type semiconductors, and electron deficient impurities are required by P-type semiconductors. For an intrinsic semiconductor, the density of charge carriers N will be equal in both cases for electrons as well as for holes, but after doping, the number density might change. Nonetheless, you need to be able to calculate the conductance of a semiconductor given some number density of charge carriers and the quantity known as mobility. Mobility is simply the efficiency term for generating current inside a semiconductor. It is the ratio of the drift velocity and the electric field. Remember, we need to apply some electric field on a semiconductor to get the charges moving. So this term basically gives us a measure of the amount of useful work done, or the charges set in motion, upon the cost of it, that is how much electric field we need to apply in order to get the charges moving with that particular speed. Ohm's law works in this case also, and we can calculate the total conductance or conductivity of the semiconductor as simply the sum of conductivity due to electrons and holes respectively. Just this one equation is responsible for half the problems from this chapter, and other topics are also important in this chapter. For example, diodes and logic gates, Zener diodes, etc. are also important, but those chapters will be very beneficial to you provided you already know those concepts well. If you don't know them well, there is really no point in starting to learn them now. If you have not done them thoroughly till now, I suggest you skip those concepts and focus on the kind of concepts that you might be framed numerical questions from. Yes, you can learn the truth tables of logic gates, and if you just know that much, then all logic gate problems will be very easy, like free marks for you, if you simply know how each logic gate behaves and for what value it will return a high output, for what value it will return a zero output. If you simply know this much, then every question from semiconductors will be very easy to you. But most questions revolve around calculation of conductivity in some way. So that was our entire syllabus in physics. I hope that this gave you some insights on your revision, and whatever notes we have made in this chapter, you can actually pause on every page and take a screenshot and keep it with you for revision. You can use these notes sort of like a formula sheet that you can just simply revise before giving any particular exam. All right. So remember, you have very less time remaining. Keep whatever knowledge you have inside your head itself. Don't let yourself get distracted. Don't let yourself get too relaxed. And once the exam is over, you will have a lot of time to properly relax yourself. Thanks for watching this video, and let's meet at your dream institute.